Uh-oh. Uh-oh. Okay, so I wasted a minute there just for my own entertainment. Um, so we talked a minute or two about friction. So what I'm doing is try to complete out the course as quick as I can. So the centroid is the next part. Um, and he has this kind of described in these objectives. But if you go down, um, if you know, if you have two things, you have center of mass, center of gravity, and the centroid of the body are the same thing if the material is made out of the same thing. So he goes through and sets this up and has a lot of this information like this. And there's nothing wrong with it, anything, but uh, essentially what you're doing is you're integrating over an entire volume and you're looking at the weight as it goes across that volume. If there is a density, he's got these little cubes. So if the density, something like so many slugs, or maybe I should use kilograms per meter cubed, what you'll find is multiply that times rho times d volume, integrating over the volume. Well, it ends up you find out you're finding nothing but in that particular case, you're finding the mass. And so it's kind of splitting hairs of whether you're finding the weight or the mass or the centroid of the volume itself. So he'll come in here and have this dW and go through. So you're looking at the weight. Then what he does, slides along. Now he's showing it as dm. Okay, so if you look at it, he sort of says that. He's essentially extracting out the G out of the thing. Then you can go down and say, well, I'm going to do the volume. And so you're integrating over the volume. So it's really splitting hairs on this. And not only that, you have these three that he's talked about. Then you can go down, well, here he's doing centroid of an area. As it turns out, more often than not, this is where your most interests lie, because he said he'll set you up so that the next section you'll find out if you're integrating across an area and you're looking for not the centroid but what's classified as the second moment. That's what you're going to carry with you into mechanics and materials. So Okay, and then centroid of a line, this is as if you had a wire and you wanted to balance it. Now, I don't know how you could necessarily balance it, but if you had a wire that was, say, shaped like a circle, well, imagine that's a circle. So you had a perfectly circle wire. You realize that the center of gravity of that thing is right in the center, but you can't really balance the wire right there because you can't put your finger there. So often, and that's kind of thinking of it as a line. There are a lot of times that shows up. You can have an object, hang on, you can have an object, a piece of metal, for example, sits, say, something like this. The whole thing is aluminum, and somewhere around in here is where you could balance it if you could put it on your finger, but you can't because this part is void. That doesn't mean that that doesn't mean we're going to skip those type, because you still need to know how to do those. So here he's going through that. That's a little bit more complicated. So let's go in, and I'm not trying to ignore the ones that are the wires, but I'm trying to focus right in on the ones that are most important. So here's a triangle. And if you look at it, he's wanting to find the centroid. So, and I'll break this down it seems ironic, but he does the integration part first. Then he goes down and does the summation part later. Actually, I think it should be reversed, but it doesn't really matter. So if you look at what he's got, he's taken this little gray bar, and he's identifying the centroid of that gray bar. That's pretty easy if you had something that was, 10 long and 1 wide. Centroid would sit right over here at 5, and it'd sit right here to half. So you kind of know where it is. So, for example, the X bar here is halfway of this X. The Y bar is just halfway up from this, or up here as Y. So if you look back at the equations, or instead of looking back, I'm going to scroll forward. Here, get rid of all this. His first thing he wants to know, well, let's see which one. He wants to know Y bar. Oh, that's what he said up here. So he wants to know Y bar. He wants to know where's the centroid up here. Now, of course, what you're going to find out is it sits right in here about 1/3 of the way from the left and 1/3 away from the bottom. But you're going to integrate this in this way. In other words, you take what is the centroid, you take the whole area of the triangle or whatever it is, and then you carry out this integral, where in the center of this integral is the location of the centroid of that gray strip. And I'm just redoing it because I don't want to scroll up. So in order to find that, you need to find out what that is. Let's go up here, and what you find, the gray strip just sits here right there. So as you move this strip up and down and add it up, the strip looks just like that. Now the question is, what's the D area here? So in this particular case, so you've got 2 things to deal with here. The other one's pretty easy. You've got Y bar, if you want to call it that, over the integral of D area. You can kind of just look at the area of the triangle, or you could integrate it yourself. But what is D area? In this case, it's this strip. Well, it's a dy, but you got to move over here to the right, put the dy out here. But how big is X? I mean, you could write X, but you got to have the limits. In other words, you got to have the limit down here, and the limit up here. Well, in this case, it's 0 to Y, but this is your limiting equation. So let's see. If I wanted to reverse this, I could say Y times B divided by H. And then, well, and then I'd have to put a minus sign in front of it and put a B in front of it. And so if you look down here, this is what you end up with. So this equation right here came as a result of D area. So if you look at it, I haven't completed it out. So here, I'll just complete it out. So if y were equal to h over b times b minus x, I'm looking for the x out of it. And so and the reason being is you want to get rid of it because you want the function to be a function of y right here and a y right there. So you're basically going through the process and trying to decipher these. Let me just get rid of everything now. And all you're doing is integrating. Well, if you did the same thing on the bottom, here's your D area, there's your D area. Those are both the same. Only thing you've got on top that you don't have on the bottom is that. That gives you another y. And so you end up with this, and not too surprising, it ends up being h over 3. If you did it off of the other one, you would get, in other words, h over 3 would sit right here. If you did it off of this, what you'd find is b over 3. And the centroid would sit right here in the middle of it. But the key is how you ran your bars. Did you run your bars horizontally or vertically? In this case, he did it for us, so I didn't really have a choice. And so the other one, well, these are okay too, but the other one is the square one. I mean, if you want to do the square one, that's pretty simple. He's got to have done the square one. He has not done the square one. So, and I think I put a couple of these on the homework, which is just, it's okay, but there's no particular reason to do this kind of stuff on the test, because on the test, that would be a test of whether you had a good calculator or not. That's all that would be a test of. So in this particular case, now this is a little bit more complex because he had to have determined that for a sliver that you end up with r over 3, and that's the centroid of the slice. And then you got to do this and integrate from 0 to pi over 2 and integrate dr. And so this is what he does. So that you have a key of defining your sliver, pulling it apart, and then sticking your limits in there. So he does 0 to pi over 2, sticking in his sliver. And then in addition, he has to slip in his x, which ends up right here. If he's doing x, if he's doing y, he's got to slip in the other. But I can guarantee you that they're going to be the same. And by the way, when you get into fluids, that you'll remember this 4r over 3 pi. That shows up a lot in fluid mechanics. I don't know, you don't have to integrate it, but it will show up a lot. And I don't know whether I don't think that shows up that much in mechanics and materials. This I know a triangle does. I know a square does. I don't even know why I would even do a square, because it doesn't really matter. You're looking at dx, dy. You're integrating, I don't know, but this might be good practice, because in a way, maybe I will do this. I mean, this seems like a stupid thing to do, but there's a lot of that goes on in classrooms. Let's say you had this. You already know, let's see, what would I call this? The base, or call this the base. Here. Okay. Erase. There it goes. There's your base, and there's your height. You already know that the thing is h over 2. But if you did this, and you said, I want to know y bar, it's integral of what? Y d area over d area. Well, if I chose my slivers to do like this is dy. So the d area in that case is nothing more than b times dy, because b is the base dimension. So at first glance, you may see this as being kind of a waste of time, but then in chapter 10, we'll reuse this same page. And so y bar would be nothing but b dy. And the y is going to go from 0 to h, and I did not leave myself a whole lot of room. So if I look at the bottom term, I can just extract that out. And then this term just becomes h times b, something you knew before we even came in the room. So then you're looking at y bar is equal h times b, or the area, times the integral of y b, which I could take out. The area from 0 to h. Then, apparently I can't. There we go. Then I'm looking at y bar is equal to, okay, so b, in this case, it's y squared over 2 evaluated from 0 to h times b. If I'm not mistaken, you'd have to correct me if I'm wrong. b h squared over 2 over bh, or the b's go, one of the h's goes, so you get h over 2. Big deal. You already knew that before you came in. You knew the centroid was halfway up here, halfway over here. That's not a big deal until you go to the next section. And for that matter, since they really should be combined in my opinion, I'll just go ahead and combine them. So the next thing he'll do is he'll go in here and do a bunch of these integrals. So what you'll see, the whole thing is based upon how, we'll pick one of these maybe if I have time before the day's done. Maybe that one, and we'll find the centroid of the shaded area. But before we do that, what you'll notice is you go through all this, there's a bunch of equations, a bunch of them are not exactly all that fun. Then you go into setting them up in composites, which, okay, composite bodies are where most everything happens in mechanics and materials. And maybe I should do this first. Maybe I'll just pick one just to show you they all look the same. So let's pick one that would be, I don't know, which one do you want? How about 9-1? It's the first one, so we might as well. They all look the same. I'm not even going to worry about the question. So if you look at it, your first decision is, which way do you want your bar to go? Let's just make it go like this. And I'll do it this way. I'm going to find, hang on. I'll put the picture down there twice. Here's dy. And of course, I guess I'll just go up here to y. So if I'm looking for y bar, I'm integrating y d area over the integral of d area. So I think I better address this bottom part first. Because if I address the bottom part, then I can come in and just stick a y in there. So if I look at the d area, what is the d area there? Well, it's the length from here. I can't decide here, from here to there. And so at first glance, it looks like x dy. Well, that's no good because x, I got to have that in the same form as this y. In other words, x is a function of y, so I've got to see it like that. Luckily, he gave me that. So what is that? Third power, or I could do it this way. Why did I write a 3 there? Y to the 1/3. How about we do this one instead? I like that one better here. X. So now I can take this and stick it in here because that's what I really need to actually calculate something. So d area is equal to the integral. Well, d area itself is not the integral. D area, the It's y to the 1/3 dy. Now, actually in this case, I love MATLAB. Okay, now it's not, why is it not behaving? I love it and I hate it simultaneously because it doesn't work. What is wrong with you? Okay. Main column. Let's try it again. What'd you do to fix it? Oh, really? And it just sits there? Oh, that one came through. Okay. So this one, that one's stuck. Let's get rid of the stuck one. It won't even go away. We'll just play with the real one. So that's the fake MATLAB. This is the real MATLAB. Okay, so what I'm going to do is I'm going to say, okay, in this integration process that we've got, I need a symbolic variable. That's supposed to be SYMS. So it looks to me like it's got to be a Y. So I'm going to come back and forth between these two. I'm going to look at the area. The area integrates, okay, this right here, Y 1/3 dy. So y goes from down here at 0 up here to 1. And so now let's use the real MATLAB and could integrate y, which is up to the, I'm going to do it like that, 1/3. And I can integrate with respect to y, and I get that, but I think you can also do that, and it gives you the number. So it tells me, where'd my pen go? It tells me that integration gives me 3/4. Looks kind of that way. I mean, I'm just looking at it. This looks like an area of 1. So if it was straight across, that'd be a half. So I'm going to say that looks reasonable to me. I'm okay. I'm moderately happy. I'd be happier later, about an hour from now, but so would you. So now that I've done that, I go in here and take a look at this. The only difference between that one and the upper one, the one on top, is there's a new y in there. There's another y. That's it. So you go in here and you say, well, okay, now I have y bars equal to the integral of y d area. Yeah, it's over 3/4. But now if I just take this integral, copy it, put a new y on there, y times 1 d y, not d area. Okay, dy from 0 to 1 as well, and then 3/4 underneath. And go back to the good MATLAB. And this time, it may look funny, but I'll just say this. Y times that. Now I got 3/7. So 3/7 over 3/4. Is that 4/7? Well, 4/7. It can't be 7/7 because that'd be at the very top. Couldn't be 3.5 because it is a little above there. So I'm going to go with that. And I can bet you money that the X bar is the same thing, although I better not. I better find it out. But here, okay, this is problem F9-1, and it's on page 465. And I'll come back and do it a different way in a second. Okay, 465. F9-1. Okay. Oh, geez, I don't know what is, okay. Here. 0.5714. That's this. I got, that's this one right here. 0.571 and then a 4. So let's look at the other approach. There it goes. And since that became busy, I'll go down. Okay, I'll go down here. Put the picture down there again. Now, let's do it. Okay, let's do it the oddball way. This is, okay, I'll still use the bars here. Now, watch why this is oddball. Okay, now I'm using the bar to the a horizontal bar, and I've still got all this stuff here. So essentially, D area is equal to the same thing, y to the 1/3. Okay, let me just make it so I can view up there. However, and I still get this same thing. In other words, the area is equal to 3/4. But now, if I'm looking for x bar, it's at the integral of xd area over the integral of the d area. If my bars go from left to right or horizontal, I can take this and stick it in with this, and I immediately have a problem. And it's not a bad problem. This still ends up being 3/4. But let's look at how this problem manifests itself. X, y to the 1/3, dy over 3/4. Now, I got a big problem. I got an x here, and I got a y here, and I got a dy. First thing is, this isn't going to go. The reason it's not going to go is I know good and well that's a function of y. So I got to put it in a function of y. So it turns out you go back to the same thing there. How is y a function of x, or how is x a function of y? I don't know. This time he has x, do it again, 1/3. So what happens to this upper integral is it becomes y to the 1/3 times y. If I did this right, 1/3 dy over 3/4, and it's going from 0 to 1. So I just changed this component. That's it. Okay, so let's see if I can make MATLAB do that. Okay, before I had the y, so now here, might as well do divided by 3 times that, and I get 3/5. So he says x bar is equal to 3/5 over 3/4. That's weird. So that shows 4/5. That's not right. Am I seeing that wrong? What is 4/5? I don't think that's right. Ooh. Okay. Well, I've made a grandiose error, though. What error did I make? I made a big error. Okay, let me show you where the error is. And this is a good example of, let's look at the book and let's see what he's written on page, let's see, 465. So this is a good opportunity, since I've made this error, to find out exactly what I did wrong so it makes good sense. Roll, 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 all the way to the top. Maybe make it a little smaller too. So here you go. So what he's saying here, let's look at this particular case. Looking at the centroid of an area. If you notice what sits in here, it's this thing that he's labeled x tilde. Now, he doesn't really describe it very good here until you get to the example. He does make an attempt right here, but I don't know. Okay. Oh, he does have a picture. 95C. Let's find 95C. Where's 95C? 95. Oh, there it is. So in other words, look at what happened here. You got a strip. You're identifying the centroid of that strip. Pretty easy here. The centroid of that strip is exactly there. If I'm coming across to the left, the centroid of the strip is halfway over. Does that make sense? So in fact, my error originates from the fact that this should be, see, the X identifies it all the way to the right end. This is the X tilde, which is nothing more than halfway out there, if that makes sense. If that's the case, then I can basically write this half out on the outside, and then I can carry through with it. So my integration may have been correct, but when I saw the answer, I realized I forgot that one half term. And the reason being is, if you look back at the book, is that when you look at these strips, how you set the strip up, for example, if you made the strip vertical, it's very conducive to finding the X bar there. If you make the strip horizontal, it's conducive to that. However, if you've already done the strip one way, you might not want to do it the other way. You got to look at these particular cases. The centroid of this strip is halfway to the length of that strip. That comes into play a lot in finding composite. So in fact, it turns out, I guess I could put the half right there, and then I could just carry the half right there, and that would be 0.4, which is the answer in the back. So, so there might be, I think, I don't even, well, I guess I could check, couldn't I? No, it's right here. There's a set. Okay. Oh, they're hidden off to the side. Here. I don't know. Nope, not there, not there, not there. Don't tell me I didn't do any integration. Oh, you guys, y'all lucked out. I didn't do an integration. And am I seeing that right, or is there a page with nothing on it? Oh. Well, okay, so there's a nothing page, and there's no integration at all. I didn't make you guys do any integration. Well, I shouldn't have done that. So I don't know why I did the integration there. So let's look at composite sections. Okay, so in composite sections, basically set themselves up in a way. Okay, let me get there. That look kind of like integrations. If you go, let me do the areas first. Okay. Okay, so does he have the set for areas? Maybe he does not. They all look the same. Trying to get to the one that, nope, he doesn't. That's weird. Why would you not do that? Okay, well, let's try to resolve this then. Okay, so don't know why. Okay, so he looks like he only shows that equation, right? As it turns out. The same thing could be said if you said X bar is equal to the sum of the x tilde times the area times the sum of the areas. This is going to be used more often than the weights. So if I had an object, say, that sat like this, and it was one, say one, it was a half, and it was one, and I had two parts together. Now I wanted to find the centroid. The first thing I can tell you is I know exactly, let's label each one of these. This would be A, and this would be B. I know exactly the centroid of A. It's basically going to be a half. The centroid of A is going to be a half as well. Centroid of B, x bar of B is going to be 1 plus a half, so 1.5. So if you're looking for the distance from here to here, that's 1.5. If you're looking for YB, it's just going to be a quarter because it's halfway up to that. So I tried to make that erase. So the question is, how would you find the centroid of the composite if you were given this and you were given that? First thing you have to do is realize, okay, the sum of the areas, well, the first area, the area of A plus the area of B. Geez, that's easy. 1 by 1 plus 1 by a half. So it looks like to me I got 1.5. So that's the area of this whole thing. I got an area of this thing, that's that, and then I got the area of this blue thing, which is that. So then the next key is, how do I deal with the stuff on top? And there's a more organized way than what I'm doing right now, but okay, there we go. But we'll add that more organization later. So if I were to look at it, let's say I were finding x bar of the thing. Well, x bar of A times the area of A plus x bar of B times the area of B, all divided by, because all I'm doing is following this, all divided by the sum of the areas, or area A plus the area B. Turns out all I do is I borrow my values from here and here. And so what I do, XA is just a half times the area of A, which is 1 by 1, which is the same thing that was right here, plus XB, which is 1.5, times the area of B, which is that. Actually, that doesn't look very good here. You know what I'll do? Instead of 1.5, how about I do it that way? So, because the 1 looked funny. Times the area of B, which is a half, all over that same 1.5 or 3/2. So if you want to look at it and figure that out, did that thing ever come up? Never did. Won't go away. So the top would be 1/2 from this plus, am I seeing that right? 3/4 from that, and then 3/2. What is that? I have no idea. I don't feel like. And divided by 8.33. So x bar is equal to 0.833. I said that wrong. Let's see right off. Let's see, 1.5. It can't be 1 if I increased, let's see, if I increased the size of B to the point where it was this big, its exact value would be 1. So we're a little bit shifted left because of the heaviness, if you want to call it that, or more area being in the yellow area here. So I would be okay with that one. So essentially, this is the way composite sections work. You just do each one in a composite. This is where most of the test exists at. And luckily, let's see if I can find this. I will make a playlist out of this, but if I go in and go to here, classes, YouTube. Okay, so I don't know that I wanted to go to the playlist. Okay, so this is another. Tell you what, let's just look at the videos. Well, maybe I should have stuck to the playlist. There are 3 in this. So this is basically one of the problems. So I'll put these in a playlist, because what happens in this is a more organized approach. You label the 3 regions, rectangular regions. It looks better if you can play it full screen. And in the sections, what you'll see is I list out A, X bar, and then I don't know that he wanted to find some information of X bar. This looks like problem 1030. So what you find out is there's 2 phases for this. And so as the page lists out, what you'll see is that you'll see the A's, then you'll see the X bar for section 1. So X bar is the distance over. Well, that looks to me like 120, and I can barely make that up, but I think that's a 40. So that means the distance over to here is 80. The distance to 2 should be 20, and this should be 80 again. And so if you do them in that table kind of sense, so that's what you see. You see this, then you list this out. You take this number times that number and put it right here. It's kind of like an Excel spreadsheet. Do that again, you add them up. You add this one and this one, you don't really care about that one. You add this one and this one, put this one underneath that one, and that'll give you the X bar. And so you see them. Okay. So this is what you see. You see this number, this one, big number. You see this number times that, big number, another big number. Then add all these up. Looks like I haven't finished writing there. So here. Okay, so yeah, now I finished writing the number. Big, long number, 1,000,000. Take this number down, take that number down. Tells you that it's millimeters, so I must be in the middle of writing the other M, because that's, yeah. So it's better to make a table like this, because it keeps it organized. Now, before I give you the impression that I'm the only one that came up with that idea, take a look at what he did in this problem. He did exactly the same thing. What he did is he had this weird shape. He decided to make this shape and subtract that one from it. And so when he subtracted it, there's a minus area there. So he created the table with the A, created, now I use the X bar in the video, but this is the centroid of the subsection, multiplies them, adds them up, gets these 2, and then he finds the location. The key here is number 3 is a hole. So it has a negative area. Consequently, it subtracts from these areas. It also subtracts from here. So I would say this table, this is the best one to look at because it has everything in it, has the table, has both coordinates and everything there. So if you look at it, that's what all you're doing. The x bars, the sum of the x bar for that particular part. In this case, his x bar runs backwards. Okay, so if you take region 1, x bar is 1, y bar is 1. X bar for segment 2, which is this, minus 1.5, 1.5 up. X bar for region 3 comes back 2.5 and up 2. You fill out that. Now what you do is you take this one times that one gives you that one. That one times that gives that. 9 times minus 1.5 minus 13. 9 times 1.5, that. 2 minus 2 times minus 2.5, 5. Minus 2 times 2 is minus 4. You just simply add them up. Then you just take this one, which you add this one up too. Take this one and slip under that one. That gives you this. Take this one and slip under that one. That gives you that one. And that's it. So if you do this table like that, which is why on the videos, that's the only way I do it, is with these tables. Then what happens is we come back and we do chapter 10. In chapter 10, we're doing what's called the second moment. And we'll start in, today is Wednesday? Okay, so we'll do the second moment stuff on Friday. And what you find out is you may look at it and you may say, oh God, no, it's not that bad. All it is when you had, okay, hang on. So x bar is equal to integral of x dA over integral of dA. Now let's just ignore this part and say x bar integral of dA over here, and we'll focus on this. We're focusing on this. What happens then in chapter 10 is he says this, there's a new term, and that's all it is. And he names it. And that's all he's doing. So then you're doing this integral. That's all you're doing. The reason this comes into play is this term right here becomes very important. And let me give you a context where it becomes important. If I can scroll down. If you're looking at a beam and you have a big moment on it, this is the same thing as saying I have a stress diagram that's like this. For example, if I'm jumping up and down on something or I'm putting my weight on it, it could be that the beam is deflecting like this. Now, this is an overboard. Turns out if you're standing here and pushing on it, common sense would tell you that this is in tension and this part's in compression. It turns out that's exactly what happens. You'll develop a relationship which you take this moment, which we learned from that last section, and you'll say, well, the maximum stress here is M, and depends on who writes this, whether it's a Y or a C, over I. And that I is exactly the term that we see here. Although you see no evidence that this is going to be used in this way later on, it does actually get used that way in mechanics of materials. So when you see that I mean, you'll see it, we'll do some problems, but it's not going to fade from your memory. You're going to be stuck with it again and again and again. And that's what I'm trying to do, is just try to make sure at least you have the ammunition when you get in there. So that's it. It's exactly time to go. No difference. So you got exactly your money's worth, which is all of maybe $1, maybe 50 cents. Oh, you probably paid more than that.